Swayam Prabha. Digital India. Educated India.
Next, we are going to look at even more generalized version of the Hooke's law, right? So until now, we have looked at the generalized version of Hooke's law for a body which is under a state of this triaxial state of stress. You have the sigmas, sigma x, sigma y, and sigma z, right? No shear. So what we are going to look at next is that how does the Hooke's law change, right? Or what are some of the additional components which gets incorporated when we also have shear along with the axial loading, which we had looked at before, right? Now, coming back again, revisiting to what we have looked at before we go ahead and include the shear, is that we had looked at this one, right? For in the case where we just have only the axial loading, we had seen, and if you remember, that these formulas, although they look slightly complicated, they're actually quite easy to derive once you get a hang of it, once you write it out a couple of times, and more importantly, you understand that how they are being derived, right? So once you write it out a few times, and you will see it slowly, gets into your system, that how these different values of the strains which are coming over here, right? So if you recall, we had applied the principle of superposition, where we had broken up this one into a cube which just has sigma x and sigma y and sigma z, and eventually we derived this set of expressions over here for the normal strings, right? Now, what is going to happen towards the end of this lecture, you will see that I am going to throw at you a lot more equations in addition to these ones which you have over here. But again, as I said, once you understand how they are derived, it's very easy to get a hang of things of how the strains or the stresses come out as, right? Now, why do we need to consider, in addition to these axial loadings, why do we need to consider shear, right? The short answer to that is any body, any particular body that you are looking at over here, right? If I am subjecting, in a particular configuration, if I'm subjecting it to different kinds of loads or the forces and so on, and if you take a small element within this particular body, it need not only have the axial loads, it will have the very general state of stresses, where it will have the sigma x's, the sigma y's, the sigma z, it will have the shear across all the different faces and so on. So that is the most generalized state of stress that you can have, right? What I'm looking at is something like this. If you have a body which is subjected to, different kinds of loadings, P1, P2, P3, P4, it may have, its own self weight, it can have some distributed loads over here on the surface, it can have loads which is distributed across the entire volume and so on. And if I take this body, and if I cut a section, say, which is normal to this x direction over here, you are going to see the sigma x, tau xy, tau xz. For the same point, if I cut another cross section over here, you are going to see the sigma x, tau yx, and so the tau xy and the tau xz and so on. So for the same point, if you take any point within this particular body over here, you are going to see all these different state of stresses which are there, right? So this is the state of stress at any point inside. So remember, initially, earlier we had only looked at my sigma x, my sigma y, my sigma z, right? Now remember, here there are the equal and opposite sigma x, equal and opposite sigma y. It is just not shown in this particular figure, right? Now in addition to that, what we are going to look at now is that what is this tau xy, tau xz, right? Tau yz, tau zx, and the the different taus which are here, which are acting in this particular member. Now remember one thing, that what we had derived, remember that when we are looking at in the concept of stresses and strains, when we're looking at that particular topic, that we saw that the taus which are occurring in these mutually orthogonal faces over here, when you're looking at a particular plane, they are equal, right? That is essentially tau xy is essentially tau yx, tau yz equals to tau zy, and so on. So what I was hinting at is that if you have this particular cube, as you see over here. So this is my tau over here and this is my tau over here, and if I'm looking at this cube in this particular diagram over here, I have this tau. So this is the tau y of x. And why is it y of x? Because it generates in the plane over here, which is perpendicular to the y-axis, and it acts along the x direction. See, this one is generated on the plane which is the perpendicular to which is in the y, but it acts along this particular x-axis that you see over here. That's why this is called tau y of x. If this is not clear, I will probably write this slightly bigger. So this is tau y of x, right? Similarly, this one is called tau x of y. And why is it called that? Because this one generates on the plane to which the normal is the positive x. The normal to this one is along the positive x, and the stress, the shear by itself, acts along the positive y direction over here. So this particular guy is tau x. The first subscript is along the normal plane. So the normal to this face is this x direction over here, and the second subscript y is the direction along which the shear is acting, which is the positive y direction over here, right? Now remember that for this one, what we had derived, that this and this tau must be equal over here to maintain equilibrium of that element, right? And to maintain for the balancing of the moments and so on. So what this essentially means is that my tau xy must be equals to tau yx, right? Now going back to my basic relationship between tau and the corresponding strain. Tau is the shear stress, the corresponding strain gamma, which is produces over here, right? Now remember, if this is called tau xy, so the gamma is the gamma is going to be called gamma xy. And do you remember the relationship between the shear stress and the shear strain? It is going to be tau xy equals to g gamma xy. We had looked at this one over here, right? So this was along the xy. Now let's look at the other direction. So if you have a tau yz and a tau yz, this is tau zy, but and now we know they are going to be equal, right? Tau yz and tau yz over here. Remember, for this one, if you're going to consider the the angle of deformation, right? You had the gamma xy over here. Here the angle of deformation is going to be your gamma yz, right? So in this one, if I have to write, it is simply going to be my tau yz will be equals to g gamma yz, right? Similarly, for the last one, which is tau zx, I am going to have my tau zx will be equals to g times gamma zx, or xz. It's one and the same thing over here, right? So what we just did was that we wrote the expression for the stresses. So the expression for the strains is simply going to be gamma xy will be tau xy by g, right? Here gamma yz will be equals to tau yz by g, and in this one gamma zx will be tau zx by g. Simple, right? So let's go back to the generalized state of stress. This was our generalized state of stress that had both the axial as well as the shear. It has the sigma x's, sigma y's, and the sigma z. It has the tau xy's, the tau xz, and the tau yz, right? So for the axial strains, we had written the relationships of your epsilon x, epsilon y, epsilon z, right? And in the last page, we wrote the relationship between my gamma xy, gamma yz, gamma zx, right? So if I just have to expand a couple of them over here, remember my epsilon x was equals to a positive of sigma x over e, right, minus nu sigma y by e minus of nu sigma z divided by E, and so on and so forth for the other ones. And my gamma xy here was equals to tau xy by G. Right, you can go ahead and fill in for the epsilon y and the epsilon z, and here for the gamma xy and the gamma xz. Right, once we have all of these strains over here, and remember one important thing, your normal strain, that is my epsilon x, does not have the relation with gamma xy. Take a look at these two guys. They're completely independent. They depend upon separate things, different things, right? So if I have to take this generalized state of stress over here, right, and for this generalized state of stress, if I have to write the generalized state of strain, right, how does that look like? It looks something like this over here, right? As I said, I'm going to throw in a lot of formulas at your face, but now you know how to get them. Now you know what is the basis of these formulas. The first ones, the first set of formulas that you see over here are the axial strains, which we just derived, right? The second set of formulas that you have over here are the shear strains. Remember, the gamma is equals to tau xy divided by G, gamma xz equals to tau xz divided by G, gamma yz equals to tau yz divided by G, right? And all of these relate to this generalized state of stress over here, right? Now that you have these strains, you can do some mathematical jugglery. You can cancel out terms, you can separate out variables to get the corresponding stresses, right? So this is essentially the transformation that we are doing from the strains to the stresses that we have over here, right? From these expressions, you can derive the expressions for sigma x, sigma y, sigma z, tau xy, tau yz, and the tau zx over here. This is not particularly important for now. What is more intuitive and easier to remember, easier to derive are these epsilons over here. Once you have these, you can easily derive these particular numbers that are there over here, right? So now that we have this generalized state of stress and the corresponding strains in a particular element or a particular structure, next we are going to look at a particular application example. Next, we are going to look at an application example of this computation of stresses which we just saw. Okay, so let's dive in and look at a problem, and you will see that making problems on strain calculations and stress calculations using the the generalized 3D Hooke's law which we just studied, it is actually quite difficult. So most of the problems in this one are essentially quite simple. So this is the problem that you have, right? So let's again, as I always encourage you to do whenever you get a problem, first understand the system first, then look at the questions, and then try to think in your head that how you are going to tackle this problem. So what you are shown over here is a thin flat member, maybe like a plate, for example, something like this. You have a thin plate over here, right, and you have the axis which is marked. You have the x-axis and you have the y-axis going vertically up, and you have the z-axis along this particular direction, and the load is in the xz plane, right? So so suppose this is my x and this is my z, right? So your load is all on the xz plane over here, and there is practically no load on the y towards the y direction. And as you will see later in the some of the later lectures which we are going to cover, this is a classic example of a plane stress problem where the stresses are only along one plane and there is no stress along the other direction, right? So if you take a look at this problem, what it says that the thickness, the plate is made of aluminum. The thickness of the plate is 3/4 of an inch, right? So which is this thickness that you have over here. So this thickness T is 3/4 of an inch, right? Within which you have a circle of diameter 9 inches, which is inscribed. So this is the circle of the diameter 9 that you have. So essentially this distance and as well as this particular distance is 9 inch, right? You're given the stresses which are acting along the sigma x. So this is the x direction, so sigma x, and to balance it out you must have the sigma x in the other side as well. So you have the sigma x along the x direction, which is a 12 ksi, kilopounds per square inch, right? And along the z direction you have the sigma z, which is 20 ksi, 20 pounds per square inch. Here are also given some other information, which is the Young's modulus E and the Poisson's ratio nu. that is 1/3 or 0.33, right? So I hope the system is clear. We have a plate on which we are applying some stresses, forces along the x direction, along the z direction, no stresses along the y direction, right? And you're given information about the material of the plate in terms of the Young's modulus and the Poisson's ratio. So let's see what the problem asks us to find. The problem asks is that what is the change in the length of the diameter along AB over here. Now, as you see in this figure, AB is along the x direction that we have over here. So we have to find the change in length of the diameter AB. So what the problem asks us to find is that what is going to be my delta AB, right? What is the change in the length in the diameter CD? CD is along the z direction over here, so we have to find what is my delta CD. What is the change in the thickness of the plate? So this thickness along the y direction, so I have to find what is my delta of T if the original thickness was T, right? And the change in the volume of the plate, so essentially that is delta V. So these are the four quantities that we have to find in this problem, right? Now, as you can probably guess, since we are given the stresses and we are given the Young's modulus, we are first going to have to calculate the strain, and the deformations, the deltas, are directly related to the strains that we have. For example, your delta AB will be what the if your original length of AB was 9 inches, you're just trying to find the delta, right? So your epsilon x is along the x direction is going to be delta AB divided by the original length of AB, and so on. So let's dive right in this problem. So for the first one, I am trying to calculate my change in length in the diameter AB, which is along the x direction. So I am going to have to calculate what is my epsilon x. Right now, we already derived, and as I said, if you write this more and more, this will sort of get ingrained in your memory. So my epsilon x is nothing but a positive of sigma x by E, right, minus nu sigma y by E minus nu sigma z by E. Right. Now, once I have written out this particular formulation, I can easily substitute the numbers which are given to me to calculate my epsilon x, right? So here, remember, my sigma x is already given as your 12 ksi, right? Sigma y is 0, there is no force for the vertical y direction, equals to 0, and sigma z is already given, sigma z is equals to 20 ksi. Right? And also you have the value of E, the modulus of elasticity, that is given, which is the same along all the directions, direction independent. It is just depends upon the material. It is 10 into 10 raised to 6 psi, right? So once you have these quantities, you can directly plug in the numbers within this one, and what you will get is the value of this particular parameter, epsilon x, right? Now, once you have epsilon x, and I'm not putting the numbers over here and computing directly, you can easily do that, or the next page I will provide the the numbers which we get over here. So once we get this epsilon x, your next step is to calculate your delta AB, right? Delta AB, remember, how is the delta and the epsilons related? I know that my epsilon x is nothing but delta AB by the original length of AB, so AB over here, so that means equals to delta AB divided by my original length was 9 inch. Remember, this information was given at this particular point, 9 inch over here. So with this you can easily calculate your delta AB. So delta AB is going to be my epsilon x, which you have calculated here, right? So times the 9 inch. So you have to be careful in substituting the numbers, in the first equation which we wrote for the strain in terms of the stresses, the KSI, the PSI, and so on. Remember, 1 KSI is 1000 PSI that you have over here. So with that, you can easily calculate this one. In a very similar fashion, you can calculate the change in length CD. Remember, CD is along the z axis over here, right? It goes along this particular z axis. So that is going to be my epsilon z. So epsilon z will again be similar kind of an equation, sigma z by E, and is related to the other stresses using the Poisson's ratio, minus nu sigma y by E minus nu sigma z by E, right? So once you again substitute these ones where this one is a 0, your sigma this will be your sigma x, not sigma z. You are given your sigma x as 12, sigma z as 20 k size, right? You can calculate this one, and this will again, once you calculate this quantity, this will again help you get your what is your delta Ct, right? The last bit is that you have to, or the second last bit is to calculate the thickness of the plate. So remember, the thickness can be, this thickness can be easily expressed. This thickness is about this y direction over here, so I have to find my epsilon y, right? So epsilon y is, in this case, is again going to be sigma y divided by E minus your nu sigma x divided by E minus nu sigma z divided by E, where here I have no stress about this y direction over here, so this is 0, and the others you have 12 and 20. So with that you can calculate this one over here, and with that you can calculate your delta of your thickness T, right? The original thickness, remember, is given as 3/4 of an inch over here, so you can calculate that, right? So that solves your this one. The last one is to compute the volume of the plate, and you can do it in two ways, equivalent ways. The first way, what you can do it, remember the original volume is what the original volume is simply your 15 times 15 times this particular thickness over here, so that is your original volume. And now after that you have calculated your delta AB, delta CD and delta T, so you have calculated the changes in length, so you can calculate the final volume, and you can do the final volume minus the initial volume to get the change in volume. The other way to do that, essentially equivalent way, that remember that we had looked at the concept of dilation, the term E which we looked at. The E was simply your sigma x plus sigma y plus sigma z, right, for that unit cube which we had looked at. And what was the what was E was an expression of your change in volume divided by the original volume of a unit cube, right? So E is nothing but delta V by V, right? So with this one also you can simply calculate that what is your delta V, because remember the change in volume is simply the delta V. It is going to be E, which you calculate from this particular equation, times the original volume, where the original volume, as we just figured out, it is going to be 15 times 15, so the length into the width times the height times T, right? So you can simply substitute these numbers and you can calculate all of these questions which are over here, right? So in the next page I have given the solution for this particular problem. So as I said, that your epsilon x, you calculate the epsilon x's, you substitute the numbers carefully. You have to be careful of the units that you're calculating, right? Now you calculate your epsilon y and epsilon z in a similar fashion. Now once you have these epsilon x's, this is the relationship between your the change in length to the original length, which is your each of these epsilons. So to find the change in length, you multiply the epsilon with the original length, d, which is the diameter for this AB and the CD, these inscribed circles that you have over here, right? And the last one is this delta T, which is the change in thickness. So that's how you calculate these numbers. Please compute on your own, and if you see get the same numbers or not, and while you're computing you will see that whether you are messing up with the units anywhere. So that gives you this box that you see over here. And then you have the change in volume. You can simply calculate the final volume after you have the change in the length, and then you subtract the original volume, 15 times 15 times the T, or you can simply calculate the dilation E over here, and you calculate the change in volume as simply as a product of E times the original volume. So I hope this problem was clear to you. Solve similar problems on your 3D Hooke's law, where you have different loading conditions on different kinds of structures to find the stresses and the strains and so on. Now that we are acquainted with the 3D version of the Hooke's law that incorporates the axial stresses, the shear stresses, the axial strains and the shear strains, and as well as the Poisson's ratio, and we derived all these different relationships between the strains and the stresses, and we can do the transformation, right? Next, what we are going to look at are two special cases of these different instances of the stresses and the strains. These are known as the plane stress problems and the plane strain problems, and you will see that many of the engineering problems that we work with on a day-to-day basis can often be categorized into plane stress problems or the plane strain problems. And in this lecture we will learn that what kind of scenarios or in what kind of cases a problem can be classified into a plane stress or a plane strain problem. Now, before we go ahead and do that, I just want to jog your memory into the 3D version of the Hooke's law that we looked at, right? So this is what we covered in the previous lecture, that when we have both the axial case as well as the shear case, right, in that particular instances I can write my axial strain as these are the three primary axial strains that I have, and these are the three primary shear strains. Now remember, the axial strains, for example, sigma x is not only dependent upon your epsilon x is not only dependent upon sigma x, but it also depends upon the stresses along the y direction as well as the z direction, and they're related using the Poisson's ratio, right? Now remember that whatever you're looking at, these three different strains and these three different stresses is are the strains for the most generalized case, where a particular body that you have or a small element within the body have these strains and have these stresses, both the axial as well as the shear, acting along the different directions, right? Now, special cases, as you can imagine, two of the special cases, the plane stress and the plane strain, as I said, are essentially derivatives of the general state of stress. The general state of stress, you have the stresses and the strains acting in all the different directions, right? And two special cases of these ones where you will see the stresses disappear about a particular direction or the strains disappear about a particular direction, depending upon the type of structure, depending upon the boundary conditions, depending on the type of loading. So this is what we are going to look at, right? So let me maybe just highlight it and write it here. The two focuses we are going to have now are the plane stress and the plane. So let's look at that under which categories or which set of problems are plane stress problems and which set of problems are the plane strain problems. So let's start with the first one, the plane stress problems, right? So the plane stress problems is applicable to members which are thin, right? When members are thin and you're essentially applying the load along only one particular plane such that the stresses about the other plane vanishes, right? So for example, the one that you see over here is that this is an example of a spanner or a wrench, right? Where remember that how do these operate? So you typically have a bolt over here, right? And you take the bolt and you essentially rotate your spanner to tighten that particular bolt that you have over there, right? I don't have a spanner in my office, but maybe I can try to do a small demonstration using a similar kind of a mechanism. So for example, if this is my this is a bottle, of course, but if you are looking at this particular plane, right, the end of the bottle, suppose this is the xy plane over here, and say the end of my umbrella over here is the spanner that I am looking at, right? So it is essentially, this is how a spanner works. You essentially tighten the bolt or you loosen the bolt like that, right? So if you take a look at this one, my forces which are applying, if this is my xy plane over here, when I am rotating or when I'm pushing or when I'm pulling over here, all these forces are in the xy plane. There is no force which is acting along the z plane that is perpendicular to the xy plane over here, right? So I hope this idea is clear that how the the plane strain problem works, right? And if you see the example of the spanner which I just showed you over here, it works essentially in a very similar fashion. You have the spanner and you sort of do this kind of a motion.